Thank you, Martin, for that great introduction. MySQL indeed turns 25 years old, and of these years, last 15 years, I spent with it in different roles, but mostly related to support. Currently, I'm a principal support engineer working for MariaDB Corporation, and today I'm going to speak about dynamic tracing on Linux as a way to find and troubleshoot complex performance problems. It's probably a third the first one was by Daniel. He is also writing great blog posts about perf and stuff. Another one was from Marcos, so I'll proceed. Let me check. Does it really work? Yeah. So I will not repeat the details of my career path that ended up now in MariaDB. I just want to mention that when I joined MySQL, I wanted to be a developer. I ended up in support, and specifically in the bugs verification team inside support that still exists and managed by the same person for all this time. I spent most of my time initially checking community bug reports, and it spoiled me to some extent in a way that I'm still speaking and thinking of MySQL and forks largely in terms of bugs, problems, and similar stuff. I even got the award mostly for writing about bugs and making sure they are properly processed. But eventually I moved on to solving real-life customer problems in support in a specific way that MySQL support used to work and probably works to this day, and in a way that MariaDB support works right now. That is in an asynchronous manner via emails by answering the questions, sending instructions, and analyzing the outputs, trying to work for multiple customers concurrently, share my time and everything. So this is the way I solve problems. It's a bit specific. It's not the same as a normal DBA or remote DBA duty when you can devote days and months of hard scripting work and preparing your system for everything. So you jump onto absolutely new problem. It may be some customer that you had never seen before, and you need the best tools that are easily available and will help you to solve the problem efficiently. So this thing is what I care about. What's also great in MariaDB, specifically comparing to all other support providers I work for, is that support here is working closely, very close with developers. So there is a lot of development happens in MariaDB Corporation, and we work closely with developers of Corporation, of Foundation, with our partners from Codership. So as soon as I can present the problem our customer have or had suspect in a way that is understandable and acceptable for the developers, we can deliver the fix really fast. So this is also how I solve problems, and that's important. My previous experience also included consulting and training and everything. As a result, I've worked out a habit to create a simple presentations that are mostly like a table of content for further reading. So whenever you see on any of my presentations anything underlined, it's a link, you can click on it to end up somewhere else, and most of the details I want to speak about are carefully studied and presented by great people whom I refer to or by myself elsewhere. So please do not hesitate to use these slides that are already shared at SlideShare and will be shared by Percona as well, I hope, really soon. I will send a link at Slack chat as soon as presentation ends. So let me also state that while I'm working for MariaDB Corporation and worked for all that great companies in the past, I was never on a mission. I was not sent by any of them on any of the conferences or missions with specific messages. So I speaking only for myself. I try my best to check all the claims and stuff that I'm saying. So I have to just highlight this stuff. So this session is specifically about tracing, that is finding out what's going on somewhere in the code of MySQL or MariaDB server, and profiling, that is measuring something like memory consumption or time spent at these tracing events, at these tracing points. There are many tools for tracing and especially profiling created over the years of MySQL, internal to MySQL itself. First of all, as you can see in all the old MySQL code, every entry to the function and exit from the function is instrumented by debug outputs in a famous debug package. And if you have a debug build, you can always enable this tracing selectively at runtime. It was created by developers for themselves to understand what happens inside the server. It's one of the most important things. There are many performance counters. If you track them with time, you can get a profile. There are different logs and stuff and everything. There was contributions from outside users that are still available in some forks like MariaDB. Users start collecting statistics about user actions, tables, indexes, and everything, and famous show profiles contribution that allows you to see where the time is spent for specific queries, at what stages. Finally, starting from MySQL 5.5, my dream as former Oracle DBA and consultant started to come true. The code was instrumented and is getting instrumented more and more with every release in a way that, unlike the debug outputs, can be used in production, low impact instrumentation, when the counters are kept in memory ring buffers of a limited size, so they can be changed fast, and there is even the SQL-based interface to all these counters in the form of performance schema. So it's a great stuff. Several of my talks over years were devoted to performance schema, and I tried to use it. It was my tool of choice because of that Oracle background where there are all those dynamic performance views and things. There is also an absolutely different approach to profiling and tracing what's going on in the server by monitoring the external traffic to the server over the network. Of all these approaches, I am going to speak, and I'm recently for 5 last years, I mostly use different ones, specifically these. I use real and poor man's profilers and operating system level tracing tools. And I will try to explain why. Basically, there are three, the tools are listed here. Basically, there are 3 reasons why I do so. I need instrumentation that is dynamic, so can be enabled and disabled at customer side by customer himself when it's needed. I want the instrumentation that is lightweight, not influencing the process. In some cases, I cannot afford to attach GDB, for example, on a high-loaded server, so I need something else. I care about performance impact very much. So it must be dynamic, it must be low impact, and the third part that I care about is that the tool set I use has to provide information that developers, specifically now MariaDB developers, are interested in. And it turned out that they are interested in really low-level tracing information, either profiles or even better, stack traces. So whenever something happens, they need to know how we ended up there. And they, like I think of MySQL in terms of bugs, they think of MySQL and MariaDB code in terms of function calls and stack traces. So from the experience, it turned out that if we can provide stack traces capture the proper moments when problem happens, we can almost immediately, in a matter of minutes, days at most, get a solution, analysis of the performance problem or the fix for the bug. So that's what I'm for. As we mostly work on Linux systems for more than 10 years, and this is important, already provide a way for low impact, fully dynamic tracing at the operating system level. The interfaces and tools that were created initially by Linux kernel developers to debug and solve performance problems in device drivers in kernel itself. So we can imagine that they are as efficient as it's possible. And they, yes, indeed, they are based on mostly the same ideas as, for example, performance schemas. Or there are some memory ring buffers that are filled in with information, for example. So internally, the data are collected as efficiently as possible. Of many profiling and tracing tools, I am going to speak about ftrace, function trace, the first implementation of dynamic tracing, a bit about perf, real profiler, and then recent, I mean, appeared in the last 2-3 years, more advanced tools with lower impact and more capabilities, specifically eBPF tools and the ways to use them. Of them, bpftrace is the recent and the easiest, probably. So, why I was not able to solve some of problems, real-life problems with performance schema. First of all, unfortunately, in MariaDB, it's not even enabled by default. We may speculate why is it so. Some people say it's because of performance impact it has. And some colleagues measured it as high as maybe 15–20% and everything. There is also a cost in memory. It's not there by default. Okay, we can ask customer wants to enable it, but then we will pay some performance slowdown as a result. And still, in case of performance schema, it's not dynamic enough for my for some complex cases. It's not dynamic enough because some counters have to be enabled only at startup. It was reported once as a bug when I hit it for the first time while still working in Percona. Moreover, unfortunately, even the MySQL code itself does not include performance schema instrumentation as every other line of the code. I may not have the instrumentation where I need it. There is this bug where I've, based on my real life experience, that turned me to perf and getting stack traces for real. That was a final decision once and forever, where I found out that, for example, the statistics collection stage of query execution is not further split into specific weights. So if query spent, I don't know, 10 minutes on statistics stage, I cannot find out where exactly it was. So there are no related weights unless it's reading from disks. So some of the weights are not instrumented. And what can I do in this case? I can report a bug. Okay, eventually the code may be changed and the result will be there. But the problem was in 2016 and the bug is still not closed. So customer cannot wait for 4 years. The last but not the least, the best you can get from performance schema is statements, related stages, related weights, and maybe statements in statements if we speak about storage procedures and everything. We do not get source code stack traces, and that's what our developers ask for. It's also not that easy to use. It's just an example from the same bug report. When you would like to get the history of statement execution with all the stages and all the weights on each stage, you have to write down such a complex SQL query entire page. I do not do the thing on the fly. The C schema later added to MySQL helped a bit with that. But there are unofficial ports to MariaDB as well, but I cannot assume it there when I need it. So I have to send this big SQL, and I did it, and I've collected the information post factum after the problem happened. I had to cite the counters properly just to find out that there are not enough details just because some instruments are missing. So what do I suggest instead? I suggest to use dynamic tracing tools provided by the operating system. By the way, Linux is not the first, maybe not even the best in this regard. The first one was Solaris with DTrace. There are dynamic tracing capabilities on Windows as well, but we will speak about Linux because the majority of servers run there. So of all the performance observability tools on this chart that I borrowed from Brendan Gregg, thanks him for that, we will concentrate on this part. So on these tools, of them I had not used LTTNG, so I skip it. The rest I've used in practice. And what's interesting about them, they cover full stack. If we speak about perf specifically, we have perf statistics counters, we have instrumentation for CPU, for memory, for disk, for all the levels of Linux operating system, for kernel itself, for system libraries, and we can instrument applications as well. One of these applications is MySQL or MariaDB. So we still need to study performance problems from the operating system side. Why not to use one tool for the entire application stack? I think it's a very promising approach and it really worked well. If you need better explanation, more details, please follow the links. I will not spend time on things like that. So of dynamic tracing frameworks, there are two, at least of those I've tried to use, that still exist on modern Linuxes and can be used theoretically. And the most advanced of them, and the first of them, the father of all tracing, is a DTrace framework. Why do not we use DTrace that much these days? First of all, until recently on Linux, we were not able to do that because of the license issues. So Oracle got DTrace as a part of Solaris, and till 2018, it was not GPL, so it could not be included. People, developers had to invent system tab, try to model it after some capabilities and features of DTrace. What's good in modern Linux is that starting from Linux kernel 4.9, those dynamic tracing tools that kernel developers had to add because they could not use DTrace anyway, they are now at the same level of features as original DTrace, mostly. So if you use a modern Linux kernel, you do not strictly need DTrace. That said, you can use it in Oracle Linux. We have few customers using Oracle Linux, and theoretically, DTrace would be one of the answers to their dynamic tracing needs. I tried to remember, recall, and get new experience with DTrace in a testing environment first, because before suggesting it even to those customers who are able to use it because of Oracle Linux. And for that, I found out that, for example, for one of my testing systems, Fedora, that is modern enough and theoretically can get the patches from Oracle Linux compiled and working to some extent. I've got some success rebuilding the kernel, but then I found out that with any next kernel release, you have to do this patching and rebuilding again. So it's not practical for using at customer side, even if they use the latest and greatest Fedora. Unless it's Oracle Linux, it's nothing, and I am not an Oracle Linux user, so I cannot get experience. So 3 reasons why DTrace is no longer relevant. First of all, we have native capabilities created by Linux kernel developers with the same features. Second, problems with kernels that have support compiled in. It's only recent Oracle Linux. And third, well, unfortunately, Solaris was not that popular as it deserves for quite a long time. So people who were not able to get the experience with Solaris for years are not ready to use DTrace easily. So it's still something new to study. Why study things of the past when we can study things of the future? So that's my reasons. System tab. System tab was an attempt, first attempt to provide dynamic tracing capabilities. System trap is interesting solution that was actually used. You can follow this link and show a nice example. The main usage happened at my days in Percona. System trap allowed to find out which user or whatever processes or init or kernel or whom are sending signals to MySQL D process. Customers suffered from that the process is killed or the process got hang up signal and whatever. So system tap program allowed to capture the system call of sending signal and provide the details, which process executed that system call. So I've applied it myself as well at the customer side. For that, you have to write down a small program, STP program, that is then compiled into a loadable kernel module. So for simple tasks like finding out who sent the signal, it will be a simple model. Chances are high that it can be loaded into kernel space and it will work. But if you write a more complex program, it can be incorrect internally. It can access unallocated memory, it can loop, and as it's executed as is as kernel module in kernel context, it can crash your kernel. I've got that on Fedora 29 last year while preparing to Percona Live talk about dynamic tracing that I gave in Amsterdam. So I had to give up on system tap. First of all, it's not secure, then you may not have it again at customer side, and you do not need it because on modern Linuxes we have the same capabilities. So the capabilities of tracing and profiling are built up on having a way to define sources of information, trace points or probes. These sources of information can be classified in the following way. The classification is presented on the slide. Are they in the kernel itself? That's where the dynamic tracing started by kernel developers, or in user space. And are they require additions to the source code? Then they are static. So there are static kernel trace points, or what happened actually with DTrace when the DTrace instrumentation was added to MySQL. You have to include specific code into the source code of MySQL. And now in MySQL 8, it's all gone. So they are static in a sense that if it's not there, you as a DBA or as a system administrator can do nothing about it until you get a new version of software. I'm interested in this part, in dynamic probes that can be in the kernel or in the user space. MySQL and MariaDB is a user space program, so I'm interested in user probes. There are two kinds of user probes. Basically, a user probe is a specific code included at the beginning, at the end, or somewhere in the middle of the function, a specific address. It can be just a probe, it's usually used at the beginning of the function, or it can be a return probe when you have a way to get the result, the return from the function. So, but these are essentially user probes. So all dynamic tracing on Linux, starting from kernels 2.6, it means Red Hat 6, it means 2009, 11 years ago, started with providing event sources. The first and normal way to provide event sources on a Unix system and on Linux is to represent them as some files. So the dynamic tracing mechanism, so-called ftrace, for the DBA, for system administrator, for the user, was presented as a separate special purpose file system that has to be mounted. And then it provides in prods or Cs, depending on version here and there, some files, text files. Some files are for setting up probes, so you write information there with echo, for example, or append information there. And other files are for reading the results. So the results of data collection in the probe is somewhere in memory, but it's mapped to the files. When you read from the file, you get what was collected or what was happened. So the interesting part is first that adding probes via ftrace was performed dynamically. So there was a real code change when you register your probe. The assembler code, the byte code is changed, so that there is a call to somewhere else where your probe actually is coded and executed, some data collected or printed. The trick is, and if you're interested in how it's implemented, I suggest you to check actually this, just a second. This link by Brandon Gregg. Okay, I'm not sure. Yeah, so let me try to maximize it. Okay, I will post it later because we're just wasting time. I'll get back to these flame graphs later. So there is a way to implement it, and it's based actually on yet another tool I had not mentioned, the original GNU Profiler. Profiling with GNU Profiler was working this way. There was a stub functions, function calls. At the beginning, it's a probe, and at the end, it's a return probe. This code was generated when you compile in profiling mode, and there is nothing fancy about it. Fancy part started when there was a way invented to replace these stubs of code with either a no operation, and it's by default is done this way. So by default, these stubs are no operation, but you can dynamically substitute them by calls to some function based on what you configure via ftrace or other sources. So it's a real code modification on the fly. If we are good with timing, I will show you live. If not, just trust me or follow the links, that the program being traced with dynamic tracing is changed at assembler level. You can see it in GDB. So that's it. Access via files is so low level that in practical cases, hardly any person without some preparation is able to use it other than kernel developers, but it's not really hard. And I've got myself ready at the end of last year to do this, because using ftrace requires just mounting a file system and nothing else installed. Even per profiler is not needed. So it's available in all versions of Linux, newer than Red Hat 5, that you can find out at customer side. So it would be interesting to know how to trace something without perf if there is no way, no permission to install any packages without some security audit or whatever. So you have to mount this special tracing file system. There are many files there, I presented just a few. If the user probe, that the part I'm interested in, is added, it's an uprobe event. Each probe is a separate line, and each probe has a type, P for probe or R for a tune probe. It has a name that is based on binary and generated automatically if you do not provide it. There is a link to the binary image, and there is a memory address. So we have some two probes here as a result. How do you use it if you are brave enough to use it directly with text processing tools? So you need to know this address to add the probe to. How do you get it? It may be complicated, but in simple cases, you just apply obj dump to the binary, find the function name you are interested in, and here is the address that you have to provide. So you have the binary, you have the address. This is a enter probe, and you give it a name, DC for do command in my case. So what else is there? If you just register the probe, you will see, you will get a printout for each execution of the function, when it was executed and what CPU, and that's all. But you can additionally print some more information. For example, you can find out and print the parameters of the function call. If you know how they are passed. They are passed via registers. So in this specific case, I know the parameter I'm interested in is passed via DX register. I have to apply some magic based on experience, or you can see what perf does and then use the same approach. And I know that it's a the zero terminated string of characters. It's a query text. That was my intention. In many cases, to train myself to do this stuff properly, I try to intercept queries executed at the process level without slow log, without capturing on the Y, just one of the tasks. So whenever, if I can do it for one function like do command, I can do it for any function. If I know how to process parameters, I can print anything. So in this case, what were the actions? So I register the probe, then I say enable user probes, then I say start tracing, and at this moment specifically the code is really changed. So based on the probe, that magic happens. And then I can read the results of tracing from the trace pipe or any other sources. There are many. For call stacks, they are different. For simple traces, they are different. There are many files. I'm not going to explain all the manual, and in some cases, you have to read source code of Linux kernel to find the details. But basically, what you get, the process with this process ID running on this CPU at this moment of time, starting from when you started tracing in, I don't know, microseconds, as far as I remember. This probe at this address was fired, and the argument that I asked for was this one, here, the query text. That's it. I have a blog post explaining all these details in steps, so I will not show that. From now on, I am ready to use ftrace directly. There are better ways to do it in practice. There are tools built around this file that do it properly. Go use them. There are links for that, but I do not even need them because they may not be at the customer server. And if I'm not, it may be not even connected to the internet. Still, I can explain what to do. I can send instruction and get the tracing information I need. Now, in reality, in majority of cases, customers, after some training or showing what we can do and why we need that, do not really hesitate to install tools like GDB or real profiler perf that appeared really soon after the ftrace. And as soon as they added the so-called perf events, so the ways to measure time, so we can get a real profile. So perf is a complex tool. It has a lot of commands that you may find useful. I mostly use these 5. You've seen them in the presentations during this conference. So the most important is perf record. You can get samples, you can record probes at some frequency. So how it happens? You just read from that file at that frequency, basically, as I've shown on the previous slide. And the data are collected into some file. By default, it's perf point data file in current directory, but you can redirect anywhere with options. The file is like a raw trace. It's not human readable. If you want to read it, you have to convert it into something more readable with perf report or perf script. What else I use? I use perf top, and I'm probably going to show it to you for quick analysis. It's like a top for processes. Perf top shows you the function calls that most of the time is spent in descending order. So it's top CPU users. And perf probe is the interface to define dynamic user probes, what I'm interested in. So there are other uses for perf. Marcos explained how perfstat is used. You can get hardware counters and all that out of scope of this talk. So if I want to do something similar to what was in ftrace, I can add the probe. If I know the source code, for example, in case of Percona server 5.7, my goal was the same, to get the query. I know that, well, it's in a parameter named call data, is a somewhat complex structure, and there is a zero terminated string with a query. So in case of perf, I do not need to deal with addresses and stuff. With symbolic information provided, and this is really needed if you do not rely on addresses, unlike with ftrace. With ftrace, you can actually access almost any memory address, try to, if it's in frames of the process. So you just set up a probe on dispatch command that should print this specific parameter string. Then you record the result, then you process the recording. As you can see, quick recording had written some data to the current directory, like 0.5 MB. And when you are done with the probe, you deregister it. Same happened with ftrace, you just clean up the file. So that's it. Marcos shown how to probe for memory misses or whatever. He was probing for specific kernel function. It was a kernel probe. In my case, it's a user probe. So what you get as a result? As a result, you get the output that is very similar to what we've got from ftrace, which process ID, on what CPU it was running, how many milliseconds since starting the recording process something happened. So it's a real profile. You can understand if you have entry probe and return probe, you can find out how much time was spent in specific function call. That's what profilers really do, like perf stop. So, and all queries are there. So I captured the activity. You can control format, you can print it carefully, do a lot of things. So it's just a simple example. What else I found out? Later I tried to do the same trick with MariaDB, and I found out that I wasn't able to, I cannot access some things. When probe is not working the way it's expected, there is a verification. You will get this kind of error messages, failed to add events. So performance event was not added. I found out that I can try to access local variables. I had to read the manual, but I found out it experimentally. So the only parameter for the do command that I tried is thread. Thread is a very complex structure. I found no way to access neither thread nor elements of the structure, but while reading the manual, I found yet another interesting thing that really is a key to what I'm speaking about. I blamed Performance Schema for not having a probe on every other line in the code. With dynamic user probes, I can do that. Lines will show me to what line of the code there is just a list with relative numbering, and the code is shown. I can attach the probe. That's debug output, by the way, that is always there, just doesn't work in debug binaries. So I found out for this specific case, for example, that at line 157, I have already a well-formed query string in the packet. I found out it in GDB. So my idea was to attach a probe to this line 157 relative address to the beginning of the function and print something there. And it worked, to summarize. So I've got a bit more samples and it works. So by example, I've already proved to myself, and I hope I proved it to you, that you can attach a probe to any line inside the function as soon as lines dash lines option shows it. So any executable line, because you cannot insert something in the middle of assembler instruction. It should be somewhere in between. So when we will get every other line of the code instrumented in Performance Schema in MySQL, it's not yet there in MySQL 8, even if it's really promoted that you should do use instrumentation. It's not in third-party tools like Galera. It's even far less feasible goal to see this happening in MariaDB, because MariaDB developers do not like Performance Schema that much, and in 10.5 we only will get Performance Schema merge from 5.7. Who knows when we will get it merged from 8.0 and we will get every other line documented. Now I say, do not need that actually. Nobody needs that. You can instrument it what you need, when you need exactly, and nothing else. So this is just a reference of some old success stories by other people with perf that really helped to solve problems and was a tool of choice for key MySQL DBAs and researchers in 2010. Perf is easy to install. It's a perf package on RPM-based distribution or it's a part of Linux tool generic. Daniel Black presented it even in more details. So basic stuff that all of you should know if you need a profile or if you need to record the trace. So you need a perf record. Here there are two arguments, well, several arguments that are important. First of all, you either record a whole system profile, so you trace all processes, or in case of MySQL, that is threads-based system inside a single process, you can pass just single process ID. Now, there is a sampling frequency. If you want specific sampling frequency, you set -f option. Now it's 99 samples per second. Do not use whole numbers like 100. You can get higher frequency, but the size of the recording will be large. And specifically what we often are interested in is stack traces. So to get a stack trace, how we ended up in this probe, you need to add -g. So other options allow you to redirect the output and do all kinds of stuff. You process the output this way, perf report. So when I work with customers, I usually send this command, redirect the output and ask for the result. There is nothing for this specific case sensitive in perf report output. Moreover, it's text-based, so customer can review it. If we speak about perf data, it was already highlighted today in one of previous talks that there might be some sensitive data. Specifically, perf data collected, depending on the probe, may include register content, as I've shown you, and register content may include what you have seen, for example, the query itself, and it may have the names of the tables and stuff. So customer may hesitate to send you raw perf data, but then you should just send them perf report command and specific, only specific probe to enable and nothing else. So that's it. Now my war story. So how I was converted. I mentioned this case. The problem was really serious. On the high load in a big Galera cluster, simple query selects by primary key started to take 13 seconds, 1 minute on the high load. Single row select by primary key. What's going on? So we were not able to find out where the time is spent from performance schema, no matter how big data collection or long data collection or fast detailed we try to enable, because it's not instrumented, that part of the wait. The wait happened in statistics stage. And what optimizer should do, what statistics to collect to find out how many rows can be selected by the primary key. It turns out it's by design that in case of InnoDB there is a dive to the index, but to dive to the index, you need to get inside the InnoDB. And in that case, customer unfortunately limited the concurrency at InnoDB level. So the statistics stage was waiting to enter InnoDB QE. And here we see it. We see a function call, and we see that 71% of all samples has this stack trace. So this is where the time is spent. Now, that allowed to find out what's going on, resolve the problem by allowing unlimited concurrency. And in the process, we found out a lot of other performance problems. So that was a key step in my appreciation of perf and operating system level tracing tools comparing to anything else. So we can easily get with if we collected data with -g option, we can get call trees. It's a small part. In reality, the files will be huge. Like I really wanted to show one of them. That's a real collection that happened just recently, work in progress last week. So let me just find it. Yeah. So that's a real collection, and the trace is huge. It can be analyzed. It was a data collection for just a minute, 60 seconds with 99 samples per second frequency. It's huge. So what is my point? My point is on one of the next slides. Perf, is it a universal one-time for all solution for all tracing and profiling needs? Not really, because there are, it's not a final solution. It may be a part of solution. because of the two problems. First, the amount of data written. So as you can see from the text output, you probably can imagine that the binary collection was also huge, and it was. For example, when I tried to find out if that specific load was IO bound and enable the probe on block IO for just 1 minute, I've collected 33 megabytes. Lucky I am that it was not really disk bound, or I could collect into a different disk. But if it was, my data collection, my sampling could lead to more performance problems that it was able to resolve. And why is that? Because I have to write down this to the user space to then process. So this is a problem. Too many information is recorded back to the user space for further processing, and this may slow things down in many cases. There is an answer. As an answer, you have to do summarization, filtering, and as much as possible processing of the collected information while you are in the probe in a safe manner. How to do it is another question, but it's a goal. Another way is how to represent the data. The nice tree representation becomes unmanageable for real systems, and we have customers who run, I don't know, 30,000 connections to, so 30,000 threads and more in background threads. You can imagine how large the information is. So you have to represent it somehow. And flame graphs that were already visible during this conference is one of the ways created again by Brandon Gregg himself to represent in a qualitative manner and to give a good idea of what's going on for the performance data collected. So now I mentioned eBPF, and again, I was not the first one. So what is eBPF? eBPF is extended BPF. BPF itself is Berkeley Packet Filte. Sounds like something related to network. Yes. In FreeBSD, I remember even PF as one of the firewalls implementations. So it's originating from Berkeley. The idea was to create complex, context-sensitive filtering rules and work for tools like TCP dump, so process network packages. Eventually, they ended up with a need for special programming language that was compiled into the byte code of a teeny virtual machine, and that's how BPF ended up. The language was too non-expressive, so they introduced a better, more complex language, still for virtual machine, called extended BPF. So some packet tracing is now done by a subset or simpler language called classic BPF. So that extended BPF was for virtual machine, for assembler, for virtual machine that is close enough to machine code of Intel, at least, so that it can be just-in-time compiled. So that the prehistory. How it works now. So you write that assembler code or get it from some higher level tool. This BPF byte code produced by the user space is then sent to the kernel. Unlike system tab, eBPF tries to make sure that when you run it in the virtual machine that is part of the kernel, it will not hang and it will not access anything outside of the scope. So there is a verifier step. Then there is that virtual machine that got access eventually when the tool was developed up to version 4.9 to kernel probes, user probes, perf events, and everything that was already existing. So the code is executed when the probe fires, and the data are collected to the kernel space, to the ring buffers in memory that are called maps, and essentially all kinds of data structures with key as a way to access, like hash tables, arrays, and everything. Then when you need what was collected in the maps, you put it back with an asynchronous read call to the user space. So this program allows to pre-filter, summarize, and do whatever it can in kernel context. And if the problem is the program you try to run is incorrect, it's will be refused by the verifier step. No loops are allowed, for example. So it cannot hang the kernel by default. That's it. So there was an entire way to current state of eBPF that is presented here. Initially, the eBPF programs were supposed to be coded directly in the assembler of that virtual machine. And it was a really hard job to do, even though people still have to check that bytecode sometime now. But really soon, a so-called BPF compiler collection tool appeared. This was based on the C code that was translated into the assembler code of that virtual machine, that is LVM, on the fly. So as soon as we get a C code, you know, string processing, memory management in C code is hard. So after that, bindings were created in a higher level, easier to use scripting language like Python and Lua. And then when the fun began, so now you can just create a Python script or Lua script, attach it to the probe and let it work. So this is what happened with BCC. So people started to create Python scripts for collecting whatever metrics and whatever kind of processing. So more kinds of maps were presented, more built-in functions were added, and in the process, we ended up with quite a tool set. What else? We can check few of these tools. We can just list a probe with a TP-list tool. You can go to the GitHub and check the source code, how it works. So this is for listing DTrace probes, and I found out by using it that, for example, Fedora binaries of MariaDB does have DTrace included, unlike MariaDB own binaries. I have started to build static probes myself, just for a chance. There is a tool for the task I try to resolve with my lame scripting called QSLOR. So it does not only intercept queries, but there are two probes at the beginning and at the end of query processing. And by subtracting time, we can capture the queries running for longer than we need. So it's a true dynamic slow query log that can have any precision up to a nanosecond, as far as I remember. And it matters in some cases. So there is also a trace tool that can be tricked into capturing queries, and many more. So I've studied some of them. The last but not the least, why we had not stopped and why the development had not stopped at BCC tools. By the way, there are entire teams in companies like Facebook that keep creating BCC tools for monitoring everything, from network to disks to application software. But you need to be a developer. If you're a DBA, writing Python scripts, for some it's natural. For me, it would be a bit hard. So I would use existing tools and will be slow in developing, but I can be, just a second. Okay, sorry about that. 5 minutes. I can be much more productive with simpler tools, and this tool was later created. It's called bpftrace, and we have seen an example of it in work. Let me just skip back. bpftrace relies on a simplified pattern matching programming language like AVK. So you have a pattern, you have a filter, additional checks, and you have an action. And this is a program for BPF. So this program can be attached to different probes. And like here, to a trace point, call syscalls, it's calling some function. Here there is it's really a pattern matching. So, and there is associated program that a bit AVK-like or C-like, so you can print stuff. And there is a lot of embedded functions provided by bpftrace to simplify your further tracing. So, sorry, why it's hanging? I don't quite understand what's going on here. Okay, so basically go study the manual of BPF and check. Let me quickly switch this from full screen mode to, yeah, to something else to show a bit more. So go study the examples and see how it may work. What's important about these tools? So the point of one of the point of bpftrace was collecting stuff at kernel context, like more lightweight profiling. So I've set up a quick test and compared for simple sysbench run queries per second executed in a test without any monitoring. Then I attached pt-pmp, like attaching GDB that is also allowing to do dynamic tracing, and got a huge drop. Then it was much less impacted by perf, and this finally is bpftrace. So the impact is minimal. One of the reasons is that the amount of data is notably smaller, even though I've already pre-processed and had written them to the user space. So that's it. Finally, as I've shown in one of my blog posts, and as Marcos did today, you can produce stack traces with bpftrace as well, kernel and user stack traces. And as soon as you have stack traces, you need to represent them. One of the ways to represent them is flame graphs. Here is an example. So just go to Brandon Gregg's site. This is off CPU graph. I have a couple of, sorry, 2 minutes, a couple of live examples. So this is IO flame graph, and this is the original nice one on CPU flame graph. So it's called flame graphs because the boxes are colored in a warm color so that we can actually distinguish one from the other. So these are stack traces. The size of the box represents number of samples or amount of memory or amount of disk I/O represented by this stack frame. So we see that most time was spent, for example, in purge thread, and in purge thread it was spent in BTR search and updating hash, so adaptive hash indexes. Let me quickly complete this because I am out of time. The problems of dynamic tracing. That would be probably the last one for me. First of all, you need root access. No way other than that. So if you are using some cloud provider, you are out of luck. But if you are a cloud provider, if you are a containers provider, then the tool is all for you. Program is changed, so if you attach GDB, you may find something else. The rest, you need to have symbolic information, debugging for packages. And to summarize my own experience, I do use GDB and perf with customers all the time. I am yet to start using bpftrace because for this, majority of customers should move to recent Linux kernels. But I'm dreaming about the time when I'll be able to do it. So I'm not the only one, others people do it, they do it even for Oracle RDBMS, so for any open source database system using Linux dynamic tracing tool, I think is a good opportunity and is a must. Thank you very much. Sorry for not showing live examples, and if you can, please, if you find some problem, performance problem with these tools without in any MySQL fork, please report bugs. Thank you.